Hello everyone, welcome to the kinematics and dynamics of machinery class. In this video, I'm gonna give another example on the kinematics analysis of mechanisms using the complex algebraic method. For this example, we're gonna consider this slider crank mechanism. Like we'd have another crank which is O2A, and there is a slider here, but this link which is AB is already sliding inside this slider that is located at 0.04. But the key point here that 0.04 itself is a fixed point. In addition, for sure, there is a hinged support here at 0.2. But the support at 0.04 it is also hinged support. So what does it mean? It means that this slider itself, it can rotate in position to allow for kind of rotation. Like you're gonna see this link AB is kind of going to rotate, but in the meanwhile is going to slide through the link through the slider itself. Okay, so generally this is the mechanism, and there are some given data regarding the dimension, like the distance from O2 O4 is given by 125 millimeter, and AB length, this length is given by 400 millimeter. The ROAO2 is given by 75 millimeter, and it is mentioned here that the slider crank mechanism is driven by the crank, which is O2A, at a constant velocity. Again, the velocity is constant. It means that there is no angular acceleration for this link O2A of 60 radian per second. Radian per second indicate this is angular velocity, and there are some requirements. And the key point here that the direction of omega 2, which is this angular velocity, is given in this direction. Okay, that it rotates counterclockwise direction, and it is required to find, or let us assume that it rotates whatever, just carry on like already given by omega 2 as counterclockwise direction, and it is required to find the angular velocity and acceleration of link AB. In addition, the angular velocity and acceleration of point P. Okay, so since there is an important notice here, and it's going to be clear, especially at the end of this video, and here it is required to find the angular velocity and acceleration of link AB. It means that this omega of this link is already required. And to do so, we do have different options. For example, we're gonna discuss this one. It's gonna be clear when we discuss the position, which should be the first step. So initially, just stick to the procedure. Then I'm just gonna refer to something here through this problem. So the first step basically just we give number to the different components and links and sliders of this mechanism, starting with the ground. This is like the virtual link, the fixed link, the frame. In addition, we do have the link 2, which is O2A, so we're gonna give it a number like link 2, and we do have link 3, which is the link AB, that is already sliding through the slider, which is like element 4. Okay, and then we have to set up position vectors or loop closure equation for this mechanism, and we're gonna start with link 2. We do have a link here, and this link 2 will have a position vector, like we're gonna say that this is like R2 vector, and we mentioned that it should be projected from the fixed point going to the other free point, which is point A. Then we do have another link, which is this very long link AB, that should have like another R, so we're gonna set up like R3 for this link, R3 vector. So as you can see, we do have an open loop. So these are the two main elements that we do have. And you should keep in mind that R2, this is the position vector for the link O2A that do rotation. And the R3, it has two functions. It works for the link AB itself, that is rotates. In addition, it works like the sliding of the link inside the slider. Here, the slider itself is not moving. But instead of the slider being moving, with the slider it is fixed, but the link itself slides through the link. So there is another sliding action. So this R3 works two functions. It had two functions. It works for the link AB itself due to the rotation that describe the rotation of the link. In the meanwhile, it describes the sliding motion of the link inside the slider. So it has two functions. So it means that R3 it works for the slider in addition to the link, kind of. Okay, so as you can see, we already identified position vector for the different components and elements that we already have in this mechanism. So, but we end up with a loop that has just two position vectors, and this loop is open loop. It is not a closed loop. So to close this loop, we do have two options. The first possibility basically is just to close this line here and just connect these two fixed points, and these two fixed points, this is gonna give us like R offset or R frame for the frame or the fixed link. And we're gonna end up with R1, which is gonna be like this is gonna be R1 vector, and it's up to you. You can assume R1 going from O2 to O4 or O4 to O2, it's up to you. And we're gonna end up with a closed loop, which is gonna be this loop. The other option is to try to connect this point O2 to point B directly and skip R1 here. So we're gonna end up also with a loop, and this loop will include three position vector, and we're gonna have like R1 here, okay? But basically the loop, in case that we choose this R1, this loop is not solvable in this case. We cannot solve this loop because the number of unknowns will exceed 2, okay? So it means that we have to choose this R1, this offset distance, to be included in the loop, and we have to choose the loop in this one. Then if anything that is related or required to point B, we can, once we finish this loop, we can find it later in another time, especially for the requirement 2. Make sense? But for some reason, if you do have a mechanism, that would be another mechanism, the given information would be a little bit different. And for some reason, if you set up a position vector here, the number of unknowns, and skip this one, and the number of unknowns in this loop, you're gonna have like R5 and R2 and R3. In case that this loop has only two unknowns, proceed with this one. And you can figure out directly the velocity and the acceleration, the absolute velocity and acceleration of point B. But since this, for this mechanism, if you try to set up this position vector and try to figure out the number of unknowns, you're gonna find them that they are more than 2. It means that you have to break down this loop into another 2 more loops. Like you have to consider this loop first, because here, if you consider this loop, the number of unknowns will be just 2. It means that we can solve this loop closure equation. Make sense? Remember all the time that the number of the unknowns, it should be only 2 for any loop closure equation for position, velocity, or acceleration analysis. So that's why I have to set up R1 here as an offset distance or an offset position vector between these 2 points O2, O4, because their distance is already given as 125 millimeter. And when we investigate, as we proceed and we try to investigate the unknowns, you're gonna find that we don't have only 2 unknowns. It means that we can solve this loop closure equation. So in the beginning, I'm gonna consider just 3 position vector, R1, R2, and R3, and then stick to the procedure. The first step is just to draw the mechanism and identify these directions over the mechanism. So we do have R2 vector. Here we do have R2 vectors going in this direction. In addition, we do have R1 vector. In addition, we do have R3. And remember that R3, it works for 2 things. It works for the link, indicate the link rotation, and also it represents the sliding motion of the link inside the slider itself. Make sense? Then you have to investigate what are the unknown, what are the given for these position vectors. So we do have R1 vectors as magnitude, and we do have theta1, and we do have R2, and we do have R3. In addition, that we do have the theta2 and theta3 for this mechanism. So how much is R1? R1, it should be the distance between O2 and O4, which is already given by 125 millimeter, and the REB, which is R2, is already given by how much? It's given by 400 millimeter. So it means that R2 is 400 millimeter, And the R1, which is the distance between O2 O4, it is 125 millimeter as given up there. But how about the RaO2, I'm sorry, my bad. RaO2, it should be 75 millimeter, but the RAB is 400 millimeter. The RAB, we don't need it, we just need A to O4. A to O4, we have no clue how much is this value. So what does it mean? It means that R3 is unknown. R3 here. This one is 125 millimeter, but this one is the 75 millimeter. The 400, we're gonna skip this value for now, and we do have this one is unknown. How about theta 1? Theta 1, it should be the angle for R1. If you try from the start point to draw a horizontal line going to the right, then rotate counterclockwise, there is no angle that we're gonna get for the R1. It means that theta 1 will be 0, and intuitively this theta 1, it should be constant. We mentioned that the direction or the angle for any offset distance like this one, because this R1 won't gonna rotate anyway, because it is a link that is, or position vector that is set up between two fixed points, so there is no possibility for this R to increase or decrease. In addition, their angle will be constant, so it means that R1 as well is constant and the angle is constant. But how about R2 vector? This for the link O2A, which is already rotating, it means that theta 2, it should be variable. And how much is theta 2? If we start from the start point, this is the start point, draw a horizontal line going to the right, rotate counterclockwise, this should define for us theta 2. So theta 2 here will be 330 degrees. It should be the, if you subtract 360 negative 30 degrees, this is gonna give us, or you can use the negative 30, it's up to you, but it is better to get rid of the negative sign. So we're gonna have here for theta 2 will be 330 degrees, and it is variable. Why variable? Because this length is going to rotate. But R2, it is fixed, it is constant value, because this length of O2A is not going to change. And what else for R3? It is R3 itself, it is variable, by the way. Why R3 is variable? Because this should be the distance between A and O4. And this distance is going to change. But the length AB itself, it is fixed. But here remember that we skip this part. We skip this part from the loop closure equation. We just consider the distance between A to O4, which means that this distance should be variable. It shouldn't be constant, right? So what does it mean? It means that the R3 will be variable, and theta 3 should be the angle. This angle, it should be the theta 3 angle, which is unknown. It is not given here, and it should be located in the first quadrant, right? Because if you draw a line from the start point, rotate counterclockwise, this should give us the theta 3, and it should be unknown. In this case, it means that theta 3 is the second unknown for this mechanism, and it is variable, and the R3 as well, it is variable. So these are the given data. As you can see that we have two unknowns, so we can proceed to the position analysis. And this is what we're gonna do as the first step, is just to do position analysis for this mechanism. For the position analysis, the key idea, as we mentioned multiple times, just to form the loop closure equation. If we're gonna look to this mechanism or this loop, we do have R2 is rotating in the same direction as following R3, but R1 is in the opposite direction. So we're gonna say that we do have R2 vector plus R3 vector equals R1 vector. This is gonna give us the loop closure equation. As given here, R1 is already fully defined. R3 is fully unknown. So this is case 1, right? Because you do have the position and magnitude of the same vector, and the R2 is already fully defined. Make sense? Then what next? Your objective is just to rewrite these terms into their in terms of their exponential form. So we're gonna have R2 EI theta 2, then R3 EI theta 3 equals R1 EI theta 1. Make sense? Then we mentioned that in case that you do have one of the equations, one of the angle that is constant, and is a common angle like 0, 90, 180, 270 degrees, we do have here 0, which is theta 1, 0 degrees, and it is constant, so it is better and it's gonna be make the solution easy if you substitute for theta 1 equals 0, and this is what we're gonna do. If we substitute for theta 1 equals 0, we're gonna end up with this equation. The loop closure equation will be R2 EI theta 2 plus R3 EI theta 3 equals R1, because theta 1 is already 0, and this is gonna give us the first equation that shall be differentiated with respect to the time twice to end up with the velocity and the acceleration later, right? Then stick to the procedure of case 1. In case 1, we have to isolate the unknown position vector. This is the fully unknown position vector, completely unknown. So we have to isolate this one on one side. It means that we have to move R2 to the other right hand side with a negative sign. So we're going to end up here with R3 EI theta 3 equals R1 negative R2 EI theta 2. Then if we decided to decompose this equation into its real and or the trigonometric form, so it's going to be R3, the cosine of theta 3 plus I sine theta 3, and there is parentheses equals R1 negative R2, the cosine of theta 2 plus I sine theta 2. Then we're gonna decompose this one or split it into real and collect the real and imaginary part. The real part will be the R3, the cosine theta 3 equal, this is imaginary, equal negative R1 negative R2, the cosine of theta 2. This is gonna give us the first equation, equation A. Then we're gonna collect the imaginary terms, so we're gonna have the R3 sine theta 3 equal, there is no imaginary, negative R2 sine theta 2, and this is gonna give us the second equation, equation B. Then if you divide A over B, B over A, if we divide here B over B equation over A equation, this is gonna give us the tangent of theta 3 equals the negative of R2 sine theta 2. This should be divided by the R1, because this R3 will be cancelled, R1 negative R2, the cosine of theta 2. Then your objective is just to substitute with the values. We already have here R2 is already given by up there. R2 is given by 75 millimeter and R1 is given by 125 millimeter. So R2 is 75 millimeter and theta 2 we got it by 330 degrees, and the same angle 330 degrees, and we do have R2 75 millimeter and we do have R1 125 millimeter. If we solve this equation, so we will obtain the theta 3 by solving this equation. We're gonna find theta 3 will be obtained by 58 degrees, and this is what we're gonna get from the calculator. And if we check above what is the quadrant of this angle, we're gonna find that it is located in the first quadrant. As we identify this should be theta 3, right? It should be located in the first quadrant. So it means that the 58 is the exact value for this angle. Then if we substitute into either equation A or B, we're gonna find that R3, just substitute into the equation A, for example, with 113.36 millimeter. Okay, so it means that we finished the position analysis for this mechanism as already given here. And remember that he didn't he didn't require anything regarding the displacement of point B, so that's why we directly substituted for theta 2 by a number value. But in case that you do have, it is required to find the displacement of this point, so it is advised to start with theta 2 with a symbolic form. Then you're gonna plug the values of the theta 2 that define the two different configurations of the mechanism. But anyway, we don't have this case here, so we finished the position analysis. Directly we can move to the velocity analysis, and this is gonna be the second step. So I brought equation 1, which this is the loop closure equation for the position analysis. Now we supposed to differentiate by differentiate equation 1, we're gonna end up with, but to do the differentiation, we have to figure out which one of these r's and thetas are constants and which are the variables. So going back to this mechanism and the thing that we set up here, that all of these are variable constants except the theta 2, theta 3 and r3, they are variables. So what does it mean? It means that we do have r2 is constant, theta 2 is variable, r3 is variable, theta 3 is variable, and r1 is constant. Makes sense? So if we decided to differentiate this equation with respect to the time, r2, the first term will be constant, so we're going to have r2. This term will be theta 2 dot ei theta 2. Then we're going to add the pi over 2 here, because theta 2 is the variable. Then we do have here the derivative of two varying functions with respect to the time. So we're going to fix one and differentiate the other one. So we're going to have the r3. Let us fix the r3. So we're going to have the theta 3 dot ei theta 3 plus pi over 2 plus, now we're going to do the differentiator over the exponential over the r3. So it will be r3 dot, then we will fix the theta 3. This gonna give us this the differentiation of this term. How about r1? It is constant, so the right hand side of this equation will be 0, and this is gonna give us the second equation, which the loop closure equation for the velocity analysis. As we agreed before, it is better to investigate the different terms in terms of the velocity directions that we end up here. We got this term which should be r2 theta 2 dot, theta dot it should be omega, so this r omega 2, and this indicates that this should be for a link, and this is what we have in this mechanism. We do have r2 refers for a rotating link. It means that this should be the relative velocity of point A with respect to O2. It means that this is directly the absolute velocity of point A, because O2 is already a fixed point. So investigating this one, we're gonna say that this should be the VA relative to O2 vector, which should be the VA vector, and it should be perpendicular to the R2 vector. Why it should be perpendicular? Because there is pi over 2 angle shift here, and it should follow omega 2 direction. Make sense? This is for this component. The second component actually or the other two components both belong to the link over the slider. And we said that R3 represents two things. Represent the rotation of the link in addition to the sliding motion of the link inside the slider. So that's why we would have two terms. We would have two components of the velocity. One that is related like R omega, theta dot it is omega. So this is like this is the velocity of the link that is already related to the rotation of the link itself. So we're gonna say that, and if we're gonna go back here to this mechanism, we do have the R3 is already set up between O4 and point A, right? And somehow you're gonna find rotation, and this rotation of the link will be somehow about point O. But you should understand that this point O itself, it has like two virtual points here. 1.04 that is belong to the link, and there is another point that is belong to the slider. And the rotation of the slider, you should keep in mind, as we explained before, that the slider itself is gonna start to swing in position about point O. So this swinging motion, it is already the same as the rotation of the link about the virtual point O4. Okay, so we're gonna say that the first term of the velocity component that we obtained, this defines the velocity of point A, but with respect to O4. Which O4? The O4 that belongs to the link. There is another O4 that is related to the slider, and that's why we would have a sliding motion. The sliding motion would have another component of the velocity, which is R3 dot down, as we're gonna see. This is sliding component. This represents the sliding velocity of the link inside the slider. So that's why the first component here of the velocity, which is this component, this represents the velocity of point A, but with respect to O4. Remember that this one was with respect to point O2. And O4, which O4? O4 that belong to the link like it is a fixed point. Like it is a fixed point. Like it is a fixed point. Make sense? Vector. And this component, it should be perpendicular. There is pi over 2. It should be perpendicular to the R3. It should be perpendicular to the R3, but follow the omega 3 direction, which is theta 3 dot. Make sense? But how about this term? This gives the sliding velocity, which should be like the VA sliding. It means that the point A itself has two components of the acceleration. One is linear, that is related to the sliding, and the other one that is related to the rotation. Make sense? So that's why you would have two terms of the velocity of the for the velocity of point A. So this is like the sliding velocity of the link inside the inside the slider, and this one it should be parallel to the R3 vector. Why parallel? Because it has the same direction as R3. As we mentioned before, parallel here it doesn't mean that it should be with or against the R3. It would be the same direction as R3 or opposite direction as R3 of R3. Depends on what? Depends on the solution that we're gonna get after a while. Okay. So this is the sliding velocity, and this is the velocity of the same point, but that belong, assuming that this point is already belong to the link itself. And this is another point, which is point A still, but this point A is referred to the point O2. Make sense? So all of these are the different components of the velocity that we already have. As you can see, there are some terms or some parameters that include dots, which are three things here: theta 2 dot, theta 3 dot, theta R3 dot. So we have to figure out which one of them of these components is given, which one is unknown, which one is constant, which one is variable. So we do have the theta 2 dot, which it should be omega 2. In addition, we do have theta 3 dot, which it should be the omega 3. And we do have the R3 dot, which is the sliding velocity of this link inside the slider itself. Make sense? So going up here to figure out which one of these components it should be given. There should be one given because we do have three, so we are limited for just two unknowns. Here, the 60 radian per second, it refers to the omega 2. And omega 2, it is constant. He mentioned that it is constant. And its value is 60 radian per second, and it is counterclockwise. It means that it should be positive 60 radian per second. So here in the velocity part, omega 2 is already given by 60 radian per second, and it should be positive. But in the meanwhile, you should understand that it is constant. But how about these two components? They intuitively will be unknown, and both of them will be considered variable because he didn't say anything regarding these two velocity components, whatever positive or constant or variable. So I'm going to consider them varying over time. Then we have to decompose this equation into the trigonometric form, the cosine and the sine form. So going back here, the first term will be R2 theta 2 dot. Then we're going to open the square bracket. For this one, it is theta 2 plus pi over 2. So it's going to be the cosine theta 2 plus pi over 2 plus I sine theta 2 plus pi over 2. Plus the second term, which is this one, will be R3 theta 3 dot, then there is pi over 2. So it will be R3 theta 3 dot, then there is a square bracket cosine of theta 3 plus pi over 2 plus I, the sine of theta 3 plus pi over 2. Then the third term, which is this one, it should be R3 dot and theta 3 in the exponential term. So we have the theta R3 dot, then the cosine of theta 3 directly plus I sine theta 3. This is going to give us the third term equals 0 because the right hand side of this equation is 0. Then we have to split it or just collect the real terms and the imaginary terms. But there are some relations here or functions that we have to recall for this part. Like as we mentioned, the cosine of the theta plus pi over 2, this gives negative sine theta, while the sine of theta plus pi over 2, this gives the cosine of theta. Just record these quantities and use them here. So in the real part, we're gonna have the R2 theta 2 dot. The cosine of theta plus pi over 2, this gives negative sine theta 2. This gives us the negative of, just let me double check here, it should give us the negative sine theta, right? Yeah, so this is gonna give us the negative of sine theta 2, and this is imaginary term, skip this term, plus the R3. So basically it's gonna be negative R3 theta 3 dot, because the cosine theta 3 is gonna give us the negative of sine theta 3. Then I'm gonna skip the imaginary term. Then we have the R3 dot cosine theta 3. It should be 0, and this is gonna give us equation A. And the imaginary part is gonna be the R2 theta 2 dot, the sine theta plus pi over 2 gives positive theta 2, and plus the R3 theta 3 dot, the sine theta 3 plus pi over 2 gives the positive of cosine theta 3, and we have the plus the theta 3 R3 dot, the sine of theta 3 equals 0, and this is going to give us the second equation. So we end up with this equation that should be solved in two unknowns. So let us figure out the given data here. R2, as was given above, R2 is given by how much? 75 and 125 for R1 and 330 for the theta 2 as given here. So we do have R2 is 75 and theta 2 dot is already given by 60, and it is positive 60 radian per second because it rotates clockwise, counterclockwise direction. Theta 2 it is 330 degrees, and R3 it is given by how much? I forgot. 125, I think. Yeah, 125. No, this R1. So R1 is the 125. R3 we got it here by 113.36. So this is R3. So we need R3, which is 113.36, and theta 3 we also got it up here by 58 degrees. So we got it by the 58 degrees, and R dot it is unknown. And remember that theta dot is another unknown, so we do have two theta 3 dot, two unknowns. Theta 3 we already got it by 58 degrees. So in the first equation we do have two unknowns, theta 3 dot and R dot, and here we do have this one is 60, this R2 is 75, theta 2 is 330 degrees, and the R3 is 113.36, and this one is unknown. Theta 3 it is 58, theta 3 is 58, and R3 dot is unknown. So we do have in the second equation as well two unknowns. So we do have two equations and two unknowns. We have to solve them to come up with values of the R3 dot and theta 3 dot. Make sense? So solving these two equations for the two unknowns, theta 3 dot and R3 dot, we find that R3 dot equals negative 4,497.26. It should be the unit millimeter per second, while the theta 3 dot we got it by the negative 1.38 radian per second. Make sense? What does it mean that this sign is negative? This indicates that it should be in the clockwise direction. This is the direction for the theta 3, and remember that theta 3 gives us the angular velocity of the link, and this is related to the rotational motion of the link itself. But R3, this is the sliding velocity of the link, so this should be like the VA or the sliding. We can just give this one as VS, where the S stands for the sliding velocity of the link inside the slider, and there is negative. So negative, it means that it should be opposite to the R3 direction. It should be going against the R3 direction. Make sense? So this is for these two unknowns, and this is for the velocity analysis. The next is just to move to the. So what next? Let us move to the acceleration analysis. But there is something that I have to point here. Later we are going to discuss the directions of these two velocity components, especially the sliding velocity. What does it mean that it is going opposite to the R3? All right, so, and we're gonna discuss this point later. But anyway, these are the unknown that we got for the velocity analysis. Now we're gonna move to the acceleration analysis. So that's why I brought here, this is the loop closure equation again that we got for the velocity analysis. Now we have to differentiate this equation 2. So this equation 2 now, by differentiating equation 2 once with respect to the time, we're gonna end up with the loop closure equation, but for the acceleration. There are some of these dots that was given by constant, which is theta 2 dot. Theta 2 dot was constant here, right, as we discussed before. So what does it mean? It means that there is no time derivative for this theta 2 will be 0, but there is time derivative for the theta 3 dot and the R3 dot that we just got by the position analysis. So, and also, if you remember that we stated that the R2 is constant, theta 2 is variable, R3 is variable, theta 3 is variable, but R1 is already constant, and that's why it had been eliminated. So we do have three variables in addition to the R3 dot. So in this form, in this equation, we do have R3 is variable, theta 3 is variable, and theta 3 dot is variable. Here we do have this one is variable, theta 3 also is variable, but also we do have V2 is variable, but these two are two constants. Make sense? Because theta 2, the length 2 is already rotating. So when we do the derivative here, these two will be just constant as a common factor. So we're gonna have R2 theta 2 dot. The derivative of this one with respect to the time gives theta 2, so this will be squared, and we're gonna have here theta I, EI, theta 2 plus pi. We're just gonna add here pi, another pi over 2, so this is gonna give us a total pi. So this is the derivative of this first term. How about the second term? It is the derivative of three terms. So we have to fix one, or three functions. So we have to fix one, we have to fix two and differentiate one. So let us fix the R3 and theta 3 dot. R3, theta 3 dot. And the derivative of this one, this gives theta 3 dot. So there should be square EI theta 3 plus pi. And then we are going to fix the R3 and the exponential term. So we're going to have R3. Then we are going to differentiate this one with respect to the time. The derivative of theta 3 dot gives theta 3 double dot and EI theta 3 plus pi over 2. Then we have another third term, which we're gonna fix here. These two terms and just gonna do the derivative over the R3 will be R3 dot, theta 3 dot, and the I theta 3 plus pi over 2. Make sense? Then how about this term plus there is another term here. This is the derivative of the multiplication of two functions. We're gonna fix the first one, which is R3 dot, and the derivative of this one gives the exponential term theta 3 dot EI theta 3 plus pi over 2. And how about this one? We're gonna have the R3 double dot, but EI theta 3 equals 0. As given here, there should be a Coriolis acceleration that should show up here, and this Coriolis acceleration, it will include two terms. The first, these two terms, if you remember, that it should include R dot theta dot. So we do have one term, which is this one, R3 dot theta dot, and we do have another term, which is this one. If you sum, these are two identical terms, so we can sum them together into two. This what gives the Coriolis acceleration. Make sense? So we can rewrite again this equation by combining these two terms. So we're gonna end up with R2 theta 2 dot square, the EI theta 2 plus pi, plus the R3 E theta 3 dot square, the EI theta 3 plus pi, plus the R3 theta 3 double dot, the EI theta 3 plus pi over 2, plus this sum of these two terms, which gives 2R3 dot theta 3 dot EI theta 3 plus pi over 2. And we do have the last term, which is R3 double dot EI theta 3 equals 0. So this gives us the acceleration equation, or the loop closure equation for the acceleration. And now let us, as usual, investigate these terms, all of these terms, starting with the first term, which is R theta dot square. Theta dot square indicate that this should be R omega square. So this indicates that this should be a normal acceleration. So this is a normal acceleration, first of all. And R2, it means that it belongs to the R2, and R2 connects O2 to A, point O2 to A. It means that this should be the normal acceleration of point A with respect to O2 vector. And it should be opposite to the R2 vector. Why opposite to the R2 vector? Because of the pi term. It means that there is 180-degree shift. Okay, so this is for the first term, which is very easy term. The second term here is identical, the same thing. It also normal acceleration, because there is theta 3 dot square, which is R omega square. This is normal acceleration, but this belongs to the link, and the link connects 2 points, point A and point O4. So this should be the relative acceleration of point A with respect to O4, and you should keep in mind which O4, A4, the one that is belong to the length like it is fixed, as we mentioned. And this should be opposite to the R4. This should be, it should be opposite to the R3 vector. Why? Because of the 180 shift. Then we do have another tangential component, which is R theta double dot. This is alpha. Theta double dot alpha, it means R times alpha gives a tangential component of the acceleration of the same point, which is A with respect to O4, because it still belongs to the length, because any length that rotates, it has two components. Any point that belongs to a length that rotates, it has two components of the acceleration. One is normal, one is tangential. So this is the tangential component to the same point, which is point A with respect to O4, where A4 is the point that belongs to the length like it is fixed point. And this one, it should be perpendicular. It should be perpendicular to the R3 vector, and it should follow the alpha 3 direction. What is the alpha 3 direction? We have no clue yet, but we're gonna figure it out through the acceleration analysis. How about this term? This term gives us the Coriolis acceleration. The Coriolis acceleration, so this should be the ACR, where CR stands for the Coriolis acceleration, and this should be the vector. And as we mentioned, this like a special component of the acceleration. This acceleration basically define the type of the difference in the, like there is a virtual link between two virtual points at point O4. We said that point O4 has like 2 points. One point that belongs to the slider, there is another point that belongs to the link itself. So this acceleration describes the relative displacement and the relative velocity, and the change, especially the change in the relative velocity between these two virtual points, the point of O4 that belongs to the slider and the point of O4 that belongs to the link itself. So anyway, this is the Coriolis acceleration that we have in this problem. And again, its direction, it depends on two things. It depends on the R dot. In addition, it depends on the V theta dot, which is the omega. So what does it mean? It means that it should be perpendicular to the R dot, which it indicates that it should be perpendicular to V. So its direction should be perpendicular to the VS. What is VS? This is the sliding velocity of the slider that we got. It R dot, we defined R dot above here. R dot, we said that this should be VS, which is the sliding velocity of the link inside the slider, right? So it means that according to this definition, it should pi over 2 indicate that it should be perpendicular to the R dot, which is the VS. So it should be perpendicular to the VS but it's going to follow or depend, somehow depend on the direction of theta 3 dot, which it should be omega 3. Make sense? As we explained in the previous lecture, there is a certain, we explain how we can identify the direction of the Coriolis acceleration, and this is also what we're going to discuss through this example. How about this component? This component, it is r double dot, so it should be acceleration, linear acceleration. Intuitively, this is going to be sliding acceleration. Which acceleration? This is the sliding acceleration of the link inside the slider. So this should be like the A sliding, where S stands for the sliding acceleration of this one. And again, it is parallel to the R3 vector. What does it mean? It is parallel. This indicates that it would be in the same direction or opposite direction to the R3, depending on the acceleration analysis that we are going to do. Make sense? So these are the different components of the accelerations. Now let us solve this equation. But as you can see, there are some double dot things. As you can see, we have only two things that include r double dot, or include double dot, which are the theta 3 double dot, it is unknown intuitively, and r3 double dot is unknown. So we're gonna have two equations and just two unknowns, and our objective is just to solve these two equations for these two unknowns. To do so, we have to decompose this equation or rewrite again in terms of the trigonometric functions. So we're gonna have the first term will be r2 theta 2 dot square, and then we're gonna have here the cosine of theta 2 plus pi plus I sine theta 2 plus pi. This is gonna give us the first term. The second term will be r3 theta 3 dot square, the cosine of theta 3 plus pi plus I sine theta 3 plus pi. And so on. So we're gonna end up with this form after we wrote the loop closure equation of the acceleration analysis in terms of the trigonometric function. Then we can decompose this one or just collect the real terms and the imaginary terms. While we are collecting these terms, we have to consider these trigonometric relations. As we mentioned that the cosine of theta plus pi over 2, this gives us negative sine theta, while the sine of theta plus pi over 2, this gives us the cosine of theta. The cosine of theta plus pi gives us the negative cosine theta, while the sine of theta plus pi gives us the negative of sine theta. Just consider these trigonometric quantities and drop them here in the real and imaginary parts. So if we decided to collect the real part, let us collect the real part. So we're gonna have here r2 theta 2 dot square. The cosine theta plus pi gives us the negative cosine, the same theta, which is theta 2. Then we're gonna skip the imaginary term. We do have here the r3 theta 3 dot square, and the cosine theta plus pi, this gives us negative, so this should be negative r3 theta 3 dot the cosine of theta 3. Then we're gonna skip the imaginary term. Then we have the the negative of r3 theta 3 double dot sine theta 3. This cosine gives us sine. We're gonna skip the sine part. Then we're gonna have the negative 2r3 dot theta 3 dot the sine of theta 3. Then we're gonna skip this term. Here we're gonna have the r3 double dot the cosine of theta 3 equals 0, and this is gonna give us the equation A. Then we will collect the imaginary term. This will give us the negative r2 theta 2 dot. Here we're gonna have the sine of theta 2, negative r3 theta 3 dot the sine of theta 3. Then the negative of r, because this term r3 double dot, this has theta, so it's gonna be positive cosine. It will be positive r3 theta 3 double dot the cosine of theta 3, plus this term will be the negative the 2r3 dot theta 3 dot this should be positive cosine theta 3, and this is gonna give us the positive r3 double dot the sine theta 3 equals 0, and this is gonna give us the second equation. So now we end up with two equations that should be solved within just two unknowns. These two unknowns are anything that include double dot, which are theta 3 double dot in addition to r3 double dot. Everything is given. We already got everything before. So if we solve these two equations, we're gonna end up with r3 double dot equals a value, and theta 3 double dot will be given a value. Okay, so if we plug this data here, all of these data, and you should consider that I've substituted for theta 3 dot by negative 1.38 as I obtained it. We got it in the velocity analysis by negative 1.38. So substitute with its value with the same sign as you got it in the velocity analysis. So anything that you got before, whatever, from the position analysis, velocity analysis with the same sign, just plug it into the next procedure and next step with the same value. We got this theta 3 dot by a negative, I substitute by a negative value. The same thing for r3 dot, we got it negative 497.26. I substitute with the same value with the same sign. It is important notice that you should substitute with the same sign as you got it. Then proceed. If we substituted with this, plug this data, and we have two unknowns, which are the theta 3 double dot and r3 double dot. Even you can use the calculator to solve these two equations. We're gonna end up with r3 double dot will be negative 0.611, and the unit should be millimeter per second square, while the theta 3 double dot we're gonna find it by 149.17 radian per second square. Make sense? You should understand that this one is positive. This indicates that it is already rotating counterclockwise direction, but this one is negative. It means that it is opposite. And again, we're gonna discuss these components and these directions. Now for the velocity and the acceleration, it should be opposite to the r3 vector. This is bare as we discussed before, right? And you should understand that this gives the sliding acceleration, while this one gives us the alpha 3, which is the angular acceleration of the link as we discussed. Okay, so now we finished. We done of the position, the velocity, and the acceleration analysis of this mechanism. And now let us investigate what are the requirements. It is required here to find the angular velocity and angular acceleration of link EB. We got them, which are the omega 3 and alpha 3. We got them. We got omega 3 by negative 1.38, and alpha 3 we got it by the 149.17 radian per second square. How about the absolute velocity and acceleration of point B? It means that we have to do further work to find the absolute position and the acceleration of point B. But if we did so, basically this is gonna be a regular mechanism. It means that we're gonna set up here a position vector for RP, this RB vector. Then we're gonna solve this loop. It means that you're gonna work on another brand new problem. Like in this case, you're gonna work in this loop. For this loop, RB is completely unknown, and R2 will be fully defined. R3, which it should be set up in this case between point A and B, will be fully defined. So now you can solve this loop after we finish the first small loop here, right? Then you can proceed, do position analysis, then velocity analysis, then acceleration analysis, like you already solving a new problem from scratch. Okay, I won't gonna do this second requirement because it is intuitively you can do it. It is very simple. It means that you're just gonna repeat again from scratch, starting from the position analysis, velocity analysis, and acceleration analysis for the new big loop. But because you have to use the data that you already got from the first small loop here. Make sense? So I'm gonna skip this part. I won't gonna do it through this video. You can easily solve this one at home. If you stuck with anything, just let me know. Okay? But the thing that I'm gonna discuss now is the directions of the velocity and the acceleration component that we got. And there is a very important notice that we have to consider here. Okay, so let me bring this equation that we got down there. So I've brought these two equations. This is the loop equation for the velocity analysis, and this is the equation for the acceleration analysis. I know that it is a little bit small, I hope that you can see it, but I've just brought this one to discuss the directions of these different components of the velocity and the acceleration and represent them over this mechanism. All right, so for the first component, which is the velocity, as we agreed that the first thing that we have to represent is the direction of the angular velocities, right? We do have two lengths that rotate, which are R2 and R3. It means that for each one there should be omega, and omega 2 is already given in this direction. This is the direction for omega 2. So we do have this direction, but how about omega 3, which is theta 3 dot? We got it by a negative 1.38. If you remember, it means that it rotates in the clockwise direction. What does it mean it rotates in the clockwise direction? It means that this should be the direction of this length of rotation as omega 3. It rotates in this direction. Or, to be clear, it is better to represent just to understand how it rotates. This length rotates clockwise direction. So what does it mean it rotates clockwise direction? It means that this part going down, but this one going up, right? It rotates in this direction. So this should be the omega 3 direction, or this is the omega 3 direction that we got. Make sense? And the same direction applies to the slider. This slider, it swings in position about 0.04. Okay, so this is for this length AB. Then let us investigate the first term here of the velocity component, which is VA relative to O2. It means that I'm talking about this length A relative to O2, and this component of the velocity, it should be perpendicular to the R2 but follow the direction of omega 2. So the perpendicular to R2 is this direction. This is the normal. So it should be perpendicular and follow the omega 2. So it should go up. This should give us the VA vector, but with respect to O2. Make sense? The second term, it is VA relative to O4, that like O4 or A, point A, that belong to the length, like assuming O4 like a fixed point, it is not moving, and just point A is just rotating, right? With respect to point O4. This direction of this velocity component, it should be perpendicular to R3 and follow omega 3. So it should be perpendicular. This is the normal, and follow the omega 3. So it should go up in this direction. This should give us the VA, but relative to O4 vector. Make sense? How about the last component? This is the sliding velocity of the slider inside the link, right? And it should be parallel to the R3, and we got it negative. This is the important notice. We got it by negative 4,497.17, right? This is the value for the R3 dot as we got it down there. And we said that since it is negative, it means that it should be opposite to the R3 direction. So if I put it in this direction to be opposite, based on that, it should be opposite to the R3 direction. See, it means that this should be the sliding velocity of the slider. Wait, the VS, it should be the sliding velocity of what? Of the slider. Assuming like the linker is fixed and the slider is the one that slides over the link. So that's why we got it negative, and we said that it is opposite to the R3, assuming that the slider is the one that is moving. But physically for this system, the slider is not moving, the slider is fixed, and the one that slides inside it is the link itself. So that's why I'm gonna switch the direction of VS, and it should be in the same direction as R3. So why did I switch the direction of VS? Because here I'm talking about the sliding. If you consider VS in the same direction of R3, here you are talking about the sliding velocity of the link inside the slider. And this is what we want. This is what have a sliding velocity. The slider has no velocity, it's not moving, right? But we do have a sliding velocity of the link itself that slides inside the slider. So the negative that we got down, it was referred to the slider, assuming like the slider is the one that is moving. So that's why in case that we do have, and this is what we did in the previous example, for example, we got the slider and we consider, and we got the acceleration negative, so we switch the direction or consider the acceleration going opposite to the position vector of the slider in case the slider is the one that is moving. But here the slider is not moving, the one that is moving is the length, so you have to switch. Since you are moving to another element, which is the link, we have to switch the direction of the velocity. This is like action and reaction, kind of. Okay, so and this what makes sense. If you try to give rotation to this, if you try to give the rotation to length 3 in this direction, and you push this link in this direction, it means that this distance is going close, is decreasing. It means that the sliding is going to be pushed inside the link itself, because this distance will be shortened. Okay, so and this basically what should happen in the basically in this system. So that's why I should consider Vs, the Vs that we got in the velocity analysis, it was referred to the sliding velocity of the slider in case that the slider is the one that is moving. Why? Why would it so? Because the R3 is going to the slider, so it refers mainly to the slider. So any sliding velocity that we got, that we can get from the time derivative of R3 with respect to the time, this gives a sliding velocity of the slider. But here physically the slider is not moving. The thing that moves is the link itself. So that's why the link is going inside the slider, through the slider. So you gotta have like kind of a switch of the direction of the velocity, since we already jump or switch to another component, which is the link itself. Make sense? So that's why the correct direction of Vs, it should be parallel in the same direction of R3, not as we discussed down. What we discussed down was the sliding velocity of the slider, assuming like the slider is the one that is moving. Okay, so this is for the velocity component. We're gonna do the same. You're gonna find a similar thing for the acceleration component, especially the Coriolis acceleration. So if we consider the acceleration as we discussed, we have to identify the directions of the alphas, the angular accelerations. So here we do have only one alpha, which is theta 3 double dot, as you can see, which is this one, because alpha 2 is already 0, and we got it by the it was positive. It means that it rotates clockwise direction, so it rotates anti-clockwise direction. It means that it rotates in the opposite to the omega 3. So if omega 3 goes in this direction, alpha 3 should go down. It means that we do have deceleration, not acceleration. It means that the velocity of this link is going to decrease as we push up in this direction. Anyway, so we do have alpha 3, and alpha 3 from this side, it should be in this direction. This is alpha 3 direction. Make sense? Then the first component here, it is A normal of A relative to O2, which belongs to this link, and this normal, it should be opposite to the R2. So it should be opposite to the R2, very simple. This is gonna give us the A normal of A relative to O2, or just A vector. This is the normal acceleration. This is the acceleration component for this link, or point A with respect to O2. Then the second, or the other three term, or the other four terms, basically they are related to this link. The first link, the first term and the second term, these are like you are talking about a rotation of a link. This is the normal acceleration, this is the tangential acceleration. The normal is opposite to the R3, so we have the normal opposite to the R3. This should be A normal of A but relative to O4 vector. And then we do have the tangential component, that it should be perpendicular to the R3 going in the same direction of alpha 3. So what is R3? This is R3. The normal to R3 should be this line. This should be normal to the R3, right? And it should go in the same direction of alpha 3. So it depends where you draw this line. So for example, all of these points from point B to point O4 are pushed up, because this is the direction of alpha, right? While this other point will be pushed down, because the point of rotation is already in the middle, right? So let us consider that this line, if we consider that this line beyond or after the O4, or between O4 and B, it means that the direction of the tangential component, it should go up. But here it should be down. right? So this should be the A tangential, and this should be the A tangential of A relative to O4 vector, and this of A relative to O4 vector. Make sense? Because it looks like it rotates in this direction. This is for the first two components of the R3. Then this component, which is the Coriolis acceleration, skip this one for now and let us focus on the R3 double dot. R3 double dot should be parallel to the R3, and we got it by negative. It means that it should be opposite to the R3. Opposite to the R3 in case that the slider is the one that is moving, typically as we did for the sliding velocity. But here, the slider is not moving. The one that is moves inside the slider itself is the link. It means that we have to switch. We aren't gonna consider it opposite to the R3 because here we're gonna switch to another element, which is the link. So we're gonna consider in the same direction as R3. So this should give us in the same direction of R3. This should give us the R double dot, which is the sliding acceleration vector. So we still have only one term, which is the Coriolis acceleration, that it should be perpendicular to the Vs, but in the same direction, as the or follow the direction in the same direction of the omega 3. So this is the direction of omega 3. It goes in this direction. But what is the direction of the sliding velocity here? Okay, so are you gonna consider the sliding velocity for the link or the sliding velocity for the slider? It doesn't matter because both are opposite. So that's why if you're gonna consider the Coriolis acceleration for the slider, it will be it will be opposite to the one if you consider the Coriolis acceleration for the link itself. So here I'm gonna consider the link because the link is the one that moves. So that's why I'm gonna focus over this Vs as I identified its value, and your objective is just to give it rotation in the same direction of omega 3 with a 90 degree, as we discussed. Like assume that this is the direction of Vs as already given, as we identified this is the direction of Vs, and this should be the start point. So you have to give rotation to this Vs following the direction of omega 3. Omega 3 goes in this direction if you decided to represent the Coriolis acceleration over this side. From P to any point that belongs to P, between P and O4, its Coriolis acceleration, it will be represented here as I'm doing here, following this omega 3. So rotating in this direction, this is gonna give us the direction of the ACR vector. For any point, this should be the direction because it should be perpendicular to V3 following omega 3 for any point belong between B and O4. But how about any point here? It should be in the opposite direction. Like here, I'm gonna represent that this should be, I'm gonna represent it here. So this should be like the Vs, and this is the start point. Here, for this direction, omega rotates here, rotates in this direction. So what I'm gonna do, I'm just gonna try to give rotation to this Vs in this direction, right? In this direction. So it's gonna be basically the same direction as ACR vector for the other points here. Make sense? Because anyway, it's gonna rotate in this direction, or the link following the same direction. So that's why we're gonna have the Coriolis acceleration will be in this direction, perpendicular to the Vs following the omega 3 direction as we indicated. Make sense? So this is for this example, and we here represented the velocity and the acceleration components over the mechanism. I know it is kind of crazy if you decided to read the this sheet, this hand typing that this handout of this lecture, you aren't gonna understand anything of all of these directions and symbols unless you do it by hand. So that's why it is better when you study, it is better to reconsider and try to do it by hand, solve the same problem by hand as a practice for you. And if you have any problem with any question, just let me know. So that's it for this example or this problem. and see you in next video. Thank you.